Thank you very much. I'm coming from Greece, Demokritos University of Thrace, the Department of Chemistry. I'm an associate assistant professor, and today I would like to talk to you about a new way to use extruded polystyrene foam, which is in order to develop a lightweight and thermal insulating cement mortar materials. Talking about construction, to the construction sector, typically we use concrete. In order to make concrete, we need to use aggregates. These come at different sizes. We have fine and coarse aggregates. However, due to the increase of the construction sector, we have a substantial use of them in the construction. Typically, we get them either from quarries or rivers, and especially in the case of sand collected from rivers, we have seen that lately, due to the massive excursion of this type of sand, living organisms are threatened. On the other hand, we have extruded polystyrene foam, or you might have heard it as styrofoam. This is this blue type foam material. It's typically used in construction for insulation because it has excellent insulating properties. It is moisture resistant, it is lightweight, it has a very high mechanical strength. However, after its use, there is no way to recycle it. What we typically use, it is either disposed in landfills or it is burned, so we use energy to incinerate it, and especially when we dump it at landfills, it is due to its nature, it cannot be degraded through the microorganisms, so it stays there for a lot of years, and it's a hazard for the environment. Therefore, and especially we have found that at coastline, there is a massive amount of XPS line. So our idea is to incorporate this type of material after its usage, this waste actually, and use it and explore its possible use in cementitious materials in order to substitute sand and develop a new type of composite. In order to do that, we prepared several and study its effect. We gather XPS waste, we process it, grinded it, and we characterized it according to its particle size. And we developed several mixes, 11 mixes with varying XPS content from 0 to 100%. We substituted sand in our material. We had a mortar material, and our mortar material was composed of Portland cement, standard sand, our XPS waste, and water. We studied the fresh state properties of the material and the mechanical properties. For the fresh state properties, we did two different tests: the slump flow test, to study the flowability, and the VICAT test in order to determine the setting time of the material, so how much time does it get for the material to harden. And also we tested its compressive strength, the flexural strength of the material, and the thermal conductivity according to all of these different standards that you see in this slide. Moving to the results, we have seen that with regards to the workability, so workability is how the material flows, if it's easy to manipulate it at the fresh state. We have seen that the incorporation of the XPS actually improves the workability, so it makes it a little bit more flowable, and this is preferable in some applications. Also, we have seen that its use increases a little bit the initial setting time and the final setting time. So it takes for the material a little bit longer to harden, which is also, in some applications, we actually want that. With regards to the compressive strength, we have seen, here you can see the different XPS content that it was substituted sand from 0%, which is the reference sample, up till 100%, which is total substitution of sand with the XPS, grounded XPS waste. In all of the cases, we see that there is a decrease in the compressive strength. This was actually, we were expecting that because the XPS that we use, the material, it's a foam and sand, has a higher compressive strength compared to the XPS foam. However, what we have seen is two important things that I need to mention. First, even at 100% substitution, here, the compressive strength of the composite is much higher than the ACI threshold for structural material. So definitely this material can be used as a structural material for the construction. Also, we have seen that at low XPS content from 0 up till 30%, there is a slight decrease in the compressive strength, like 5%, this is minimum. Then at medium XPS content from 30 to 70%, there is a more pronounced decrease. And the significant decrease, reduction in the compressive strength happens at very high contents of 70 up till 100% of XPS. Looking at the flexural strength, we can see the same trend. It is interesting, the fact that while the compressive strength here decreases 46%, for the flexural strength, the reduction is much lower. It's 26%. And also we have seen a different observation in the failure mode. So if we look at how the reference sample has cracked, we have a steep crack, and actually it is a brittle failure mode. While when we are increasing the XPS content, we have seen that the material has a more ductile failure and the fracture of the material increases. Now, moving on to the thermal conductivity, which is a very important property when we're talking about thermal insulation. Materials, we have seen that it is decreasing. We want the thermal conductivity to decrease. Lower thermal conductivity means that the material can be used as an insulating material. Similar to the compressive strength results, also here you can see three different areas, from 0 to 30% substitution, from 30 to 60% and higher than 70%. What it is worth mentioning is that we have seen that for substitutions of 90 and 100% here, the material, according to the RILAM, can be classified as class 2, which means that it can be classified as a lightweight material and insulating material, as a structural, lightweight, and insulating material. So we with the use of the XPS, we can alter the matrix and make a new type of material that can actually have insulating properties. Here you can see the results of the density. Of course, with increasing the XPS content, the density is decreasing. Again, according to RILAM, for the specimens with 90 and 100% replacement of sand with the XPS, this material falls at the RILAM 2 category. It can be characterized as structural and insulating. And moving on, comparing the thermal conductivity over the density for the different percentages, substitution percentages that we have studied from 0 up till 100%. It was quite interesting, the fact that we have seen that there's a actually linear correlation between the thermal conductivity and the density. And again, here you can see the two different classifications. So this is also shows that for percentages higher than 90%, this material is structural, insulating, and lightweight. And for percentages higher than 40%, it can be characterized as structural and lightweight material. And to sum up some main conclusions, so these XPS modified mortars can maintain the workability. They are easy to work with, and they extend the setting times of the material, the setting time of the material, which is beneficial in some applications. For the mechanical performance, all of the mixes have a lower strength requirement, lower strength compared to the reference. However, it's really important to state that all mixes exceed the minimum requirements for structural use, and there is a trade-off between the XPS content and the strength. With regards to thermal insulation, for high XPS contents, 90 and 100% substitution, we have very significant improvements of the thermal insulation properties of the material. And overall, this shows that this composite could be used, and it would have a very low environmental impact actually, and the XPS waste incorporation supports the sustainability, and by that way we can produce new type of composite using materials that cannot be recycled. Thank you very much for your attention.